Just an observation where the timing is under question. We just try and figure out, is this time accurate? Could something have gone wrong? And we came to the conclusion that it all seemed fine. I don't know how many weeks you spent on the other ones, but it was a lot of effort to try and figure out, was our time actually accurate and reliable for those events? Because fundamentally, we have to have accurate and reliable timing. Mouse thing, here we go. So this was kind of initiated by some comments that Dave Gerald made about the need to understand the accuracy of the time base that he's reporting. And we're really not flowing that information through to our reporting systems. We get supposed accuracies on the D and R times on our observations, but usually there's actually no statement of what was actually the accuracy of the timing itself that was used for that observation. And we kind of realized that we had a bit of a black hole here. I was in the process of being made redundant from one job and sitting around twiddling my thumbs. So I spent some time looking at this, and this is where we've come to so far. It is still very much a work in progress. It is not conclusive. If I annoy anybody by a statement and they think that their timing device that they've spent decades working on performs better than maybe I suggest it does, my apologies. We haven't got to the end of this rabbit hole yet. But fundamentally, how can we get accurate time? How accurate is our time and how reliable is our timing? But most importantly, how can we improve? So what is time? I have no idea. Professor Hawking probably has a good idea, but I'm not going to understand it in a half-hour session, and probably none of us here are either. The really important thing is, how can we determine what the time is? What do we have to do to figure out what the time actually is? Now, to help us along with that, there's actually international units of time. So this is the standard definition. It's been in place since, it'll be on my timeline somewhere, but this defines the rate of progress of time by reference to a cesium atomic clock. So I've got a definition of how the rate of time, how fast time moves on. So we can use an atomic clock to measure the interval of 1 second to about 1 second in 300 million years, something like that. But that still doesn't tell us what the time is. What is the actual time? 1 second's passed between then and then, but when was then? You don't know. So to do that, we actually have to figure out what the actual time is. And this is where we come along and we just have to say arbitrarily, this is the time. This is the start of time. This is second 0. And that's been done by international agreement. So this is where the UTC comes in. UTC was the first major consensus definition of time, and it's a worldwide standard. It's what we all use. It's what your iPhones receive. It's what your computers receive. It receives that time and tells you what the time is. And that is distributed around the world. If we didn't have UTC and if we didn't have it accurately distributed around the world, our power would go out, our financial systems wouldn't work, you'd be down at 3G cell phone rates, planes could possibly fall out of the sky. That's how important time is to our modern society. So UTC stands for Coordinated Universal Time, basically because the French get involved with naming everything. That's based on TAI, which is actually atomic time, and something like time atomic, and sorry, forget the acronym. The two different time scales, UTC is what we use, but that has got leap seconds added to the atomic time, because atomic time started a while ago, and the Earth's rotation doesn't progress at a constant rate. The Earth is not a clock that goes around at a rate of 1 revolution per day. So we've got 2 time scales. The leap seconds are used so those time scales don't get out by more than about 1 second. But those leap seconds are going to disappear at some time, maybe by 2035. So here's the timeline of time. So modern era timing basically started with atomic time, being defined as a time scale of about 1955. Coordination of time around the world started in 1960. So it's a similar problem to what went on with the railway system in the UK, where in the 19th century, they had to figure out how to actually coordinate time across all our railway stations across a network so that we don't send trains through at the wrong time and have them crash. And they came up with some Victorian solutions to that. Atomic time was a 20th century solution for that. UTC became in 1963 the standard adopted around the world. They adopted it before the standard international unit was actually adopted, which is kind of interesting. And then things have progressed. Relativistic corrections came in 1970. I think Dave can explain the difference between barocentric, geocentric, and terrestrial time, 3 different time scales.
Yeah.
One of them is the center of the solar system.
Geocentric is the center of the Earth. Barocentric is the center of the sun.
Yep.
Sorry, of the solar system. Heliocentric is the center of the sun.
Yep.
And terrestrial is us.
Yep. You probably didn't hear that. So terrestrial is our common time, geocentric time, time at the center of the Earth. Barocentric time, the time at the barycenter, center of mass of the solar system. So those were all synchronized in 1977, which has probably been a huge help to actually doing space exploration, because otherwise you'd have different times that are out of sync between terrestrial time and all the time scales that you needed.
And I think you'll find it's relativity is the primary difference between them.
Yep, I defer to experts that know more than me on this subject. For us, a really interesting thing, 1983 is when the GPS system was made selectively available for higher precision time. Around that time, 1985 Network Time Protocol, which is NTP, Internet Server Time, that was introduced. It's one of the earliest internet protocols still in use today. That enabled time to be distributed across computer networks. So you could use a computer network to synchronize time. Because synchronizing time in different locations around the world is actually very hard to do. 1993, that's when we had the full GPS constellation from the US GPS system. And NTP as a service distributing UTC started from the National Institute of Standards and Technology in about 1993. And by 2000, that's when GPS and the PPS was opened up to the full precision. And that gives us the basis for most of our devices. As some of you recall, when some of the video time inserters started coming, that was around about 2000 when things started to get developed. So we're the beneficiaries of all this time development. Now, if you come to try and measure time, we've got a bit of a problem because it's not really an easy thing to physically measure. It's the consensus time is derived from hundreds of atomic clocks operated around the world. Most nations operate their own atomic clocks and feed into the service, and it's coordinated by the Bureau International Point de Mesure, sorry, French pronunciation, is basically weights and measures group for France. They coordinate this. They receive the times from all these atomic clocks, and then they try to figure out by consensus what is the average time, get rid of the outliers, figure out what it is, and they issue bulletins regularly. About every 5 days. There's a faster service going now. But so the point is that there's all these atomic clocks. We're trying to coordinate them, and then we send out a time so we can then kind of synchronize. So we only really know what the time is retrospectively. We don't know what the time is now. We know from people filing reports that over the last few days, that's what the time is. So there's a little bit of unsteadiness in there. But those retrospective offsets are usually quite small, a few or tens of nanoseconds. Picture there on the left is an atomic clock that you can buy. If you really want to hang an atomic clock off your astronomy rig, you can. You just have to pay for it. It's actually a lot cheaper than some of your telescopes. And on the right-hand side, that's one of the atomic clocks that's been operating at NIST. So for high precision time, they're serious scientific instruments. This is an example of one of the bulletins they put out. So what they do is they give the offsets at 5-day intervals for various stations. There's a national lab in Sydney, Lower Hutt. This is Measurement Standards Laboratory in Lower Hutt from New Zealand. That's our official time. Any NTP site time service from New Zealand is probably deriving from that. And NIST is the one in Boulder, Colorado, which supplies the time sync for the GPS satellite system. And you can see here these offsets between UTC and UTC-K, UTC-K being the lab itself, are usually quite small. This is in nanoseconds, but you can see you get departures. Sydney was out by 17 nanoseconds. Someone probably got an alert in the middle of the night around about that one. Boulder, Colorado for this period was very, very stable. Some countries have seen hundreds to thousands of nanoseconds offsets, so not every country is able to manage their atomic clock as well as NIST is able to. So each country each station has one of these. But then, okay, so these scientists and geeks know what the time is, so they have to tell us what the time is. So how is that going to happen? Diagram on the right gives a rough idea of how that happens. So we've got all these labs contributing time to BIPM of France, and then they distribute to each national laboratory what the consensus time is. And then at this point, they update their time. If they need to adjust their time, they do. From there, they distribute that time to their GPS constellation of satellites. Can then be used to be sent to ground stations, to run NTP servers, to run radio clock services and these kinds of things. The GPS constellation, that's the time source for that is NIST in Boulder, Colorado. Other GPS constellations may use different time sources. That's the high-level view of how this gets distributed. Now, the real meat and the sandwich is, how do we get our time? So somewhere between that national lab and our beautiful timestamps that enable us to do those Didymos observations, we receive the time through a wide variety of devices. Now, it's actually seems, looking at this now, with 400 roughly observers contributing observations with this number of different ways of receiving time, it's quite possible that every observer actually has a unique time system. Quite possible, if we actually dug deep into it. Perhaps not so great for standardization. I'll be talking in a workshop this afternoon about methods of PC time discipline, which also have to use GPS flashes. So we're receiving time in many different ways. So I'm a trained scientist. I've got a PhD in physics, actually a master's degree in astrophysics. I'm always concerned about how accurate are my instruments, how do we know, how do you calibrate? So how accurate and reliable are these time systems? And how can we, as amateurs, know or show or prove how accurate they are? So scientific way of doing that is to actually do some form of calibration. To actually do a calibration that traces your time back to the international standard, back to the SI units that we talked through here. So the only way that you know if a device is accurate or what the accuracy is, you can't really say something is accurate. You can say it has an accuracy because I've measured it. So you really have to calibrate your devices to be able to know that. To be considered scientifically calibrated, it has to track back to UTC. That means that your measurements can be linked back to the national and the international measurement standards. To actually do a calibration that stands up scientifically or technically, you have to measure every step in the chain back to UTC, back to SI. And you don't just do it once, you have to repeat it regularly because things will shift. Now, if your system is stable, maybe you do it once a year. If it's not that stable, you might have to do it once a week or once a day. And you can see, even those atomic clocks, they're adjusting them every 5 days. Best clocks in the world, they're adjusting them every 5 days at the nanosecond level. So that gives you an idea of traceable time. Sorry, it's a bit hard to keep hold of the chat as well. So this is some information that's put out around how these kind of reference times should be going. So you need to test regularly to ensure the performance hasn't changed. Anytime there's a change in the hardware or software, you may have to retest your device because there's no guarantee it's going to perform the same. We're actually in the low accuracy range. Technically, when you get in the low accuracy range here of about 1 microsecond, instead of having to test every single device, a manufacturer could actually do a unit test on a single device and then claim that other devices with the same design and the same manufacturing line perform to that same level. So we're kind of on this unit testing level, and we're talking maybe low accuracy because most of our measurements aren't that accurate. And there's a reference there if you want to do that. Ideally, this should be done by an accredited lab, but we'll see how we can go. So if you actually wanted to establish traceability back to UTC, these basically the steps that we go through from SI units through UTC, through the GPS system. This is where we pick it up on a user's time and device. Then we put a timestamp on something, which may need adjustments, and then we actually do analysis and reporting. So you can see there's actually quite a long chain back to UTC. If we want to claim traceable time, we actually have to trace from our user analysis and reporting all the way back up to SI units and document every single step. That will be the scientific way of doing it. So this gives an idea of basically what's going on at each point. We've got accuracies down to a few nanoseconds to the GPS. Once you get the GPS receive signals, then it's going to vary by device, vary by conditions, and the errors start to stack up. So what we don't really need to worry about is these, because this is taken care of by the national laboratories, by NIST, by the international groups. They manage all of this, they document it. The errors down to this point are down to the few or tens of nanoseconds. And we're nowhere near an occultation center to deal with nanoseconds, thankfully. So these errors are pretty small compared to the rest of them. This is where we need to start to worry about it. When we actually receive those GPS signals and start to do something with them, and I to VO time, I receive the GPS signal to its chip, puts that a pulse, and then we have to do something with to create a timestamp. Now, this is where it gets affected by local conditions, by reflections, by the ionosphere, these kinds of things. And the type of errors that can occur there are sort of 10 to 100 nanoseconds. 100 nanoseconds is 0.1 of a microsecond. So it's starting to get into the range we need to be concerned about it. Every GPS receiver behaves in its own way. It can, as a consumer of devices, not actually a manufacturer, it can be quite difficult to actually get information or documentation on this. Usually we won't be able to get a certificate of conformity saying this device complies to UTC or traces to UTC. The best we can maybe do is get a data sheet from that. So this isn't actually looking that encouraging, because there isn't really no practical way for us to measure these timing errors to the GPS receiver. It's really beyond what we could be expected to do unless you're actually some form of accredited lab. But fortunately, we've got something to save us, and that's this magic 1 PPS pulse. That little flashing light that you see on most of these GPS receivers, that's a high time precision pulse derived from the GPS. And that occurs very, very, very close to the UTC second. And this is a summary from this paper. If you're interested, go and have a look at it. But basically, they're saying if you don't correct any of these errors, then it's not going to be worse than 1 microsecond. So that PPS pulse, as it comes out of the GPS receiver chip, not as it comes out of the box, out of the actual chip on the circuit, that should have an accuracy of no worse than 1 microsecond, even if things aren't going happily in the ionosphere and your antenna's not set up properly and these kinds of things. So we can trust that PPS, if your GPS is operating properly, to be within 1 microsecond of UTC. So if our required accuracy is no better than 1 microsecond, we can make the assumption that that PPS is accurate enough. And we don't need to measure anything further up on that chain. We can get documentation from the likes of U-blocks on the spec for that PPS, and that expects like 99% of the time that PPS will be within 60 nanoseconds of UTC. So this gives us a point where we can enter that chain. So we only need to measure those uncertainties in those parts down the chain. And that's great because I'm not going to build myself a national standards lab in my backyard to try and do this. So if we want to get that unbroken chain of calibrations back to UTC, we can make that assumption that PPS is accurate to no worse than 1 microsecond. And then that's where we start to have to actually measure the delays and uncertainties in the hardware and the software that we're using to process and handle that pulse. That's where formally there's 2 types of errors that we need to consider in this calibration. The type A errors, this is the random errors caused by software or other things going on. It's non-deterministic. It's not the property of a physical device. So these kinds of things get measured statistically. There's the type B errors, deterministic errors. These are things like baked-in hardware delays from a circuit or a clock cycle for a piece of software running on a microcontroller or something like that. So if you do this regularly, then you can actually establish this train of traceability back to UTC through that 1 pulse per second. Okay, so these are the things that in principle are under our control and under our influence. So we're basically starting at point F, our user's timing device. We don't have to worry about the stuff that's before that. We still have recording timestamps and analysis and reporting. I'm primarily focusing on this user's timestamp devices, other source of errors that come in here or can come in here that we need to deal with. So we're responsible for managing these links in the chain because by and large, we're not using consumer devices that are made by a manufacturer. So when we actually look and think, sorry, I've gone too far. So when we actually dig into how our timing devices have been tested, you saw how many different timing devices there are. There's loads of different ones out there. Some have been in limited production, some are production models from like QHY, some are DIY builders and all sorts. There's only very limited testing of these devices that is publicly available, like on the internet, or appears in a publication. There's not a lot of information out of there. A lot of that is old and has not been repeated. Tony George, in one of his papers on this, said, go ahead and repeat this information. It was in 2015, and I don't know if it has been. You've probably come across some of these testing devices. Most of these are one-off. The extra, I think, is a one-off device, or DLB build or just limited production. In the process, most of the claims you'll see, most people, if they are making a claim, are asserting back to that one PPS, which is valid. But often there's not actually enough technical detail to understand, how was that testing done? What does it actually mean? And the testing may be old and may not have been done for some time. So I think it's fair to say that few, if any, of our timing devices are actually calibrated or traceable back to UTC. So we're essentially assuming that the timing is correct, but we don't actually have any evidence that the timing is correct. Now, how are we doing for time?
Yeah, keep going.
Okay. Okay.
We'll be ending lunch in 45 minutes.
Okay, I should be fine. I don't know how to get rid of that pop-up screen. So I lost my mouse again. So just to use an example, so this is just looking at information that I can find in published papers, information that I could find online from websites or whatever, or symposiums or whatever. This is basically a perspective of someone taking a look and saying, oh, here's this WATEC 19HX using an IoT video time insert. How do I know that's inaccurate? What proof is out there? Now, when you dig into it, it's got internal measurement delays. Most of you will be familiar with this. You have to use a spreadsheet to fix them or whatever. Those were first measured by Dangle in 2013 using his own extra device, which he made. He's got some information on this. He's put a little statement out there, some basic information of it. If this information stands up, then the actual inherent accuracy of the timing going into that device would be about 1 microsecond. So all he measured was the internal camera delays. He didn't actually measure a video time inserter. Tony Barry and others. Tony Barry was involved in the development of the Sexta device, which is another GPS flashing measurement device. He actually measured the time and accuracy of an IOTA VTI, one model of it, because there's multiple models which could behave differently. But he was using a WATEC 120M. So we've kind of got two pieces of the puzzle. We've got the measurement of the IOTA VTI and the measurement of the 19AX, but it was done with a WATEC 120, which is a different camera. So we can't really link those two things together, unfortunately. Now, in the paper on that device by Tony Barry, there was actually a pretty good statement of how they measured the delays from the PPS. They actually went through with an oscilloscope, measured the delays from the 1 PPS pin to the various processing steps, and it's about 0.165 millisecond delay there. So there's actually pretty good evidence that the Sexta device will be accurate to the 2 milliseconds that was claimed. So the testing device they used sort of seems to stack up, but there's actually no link here. We can't use this to make a link back to UTC because things are not connected. We're not using one device into another device and into another device. So they're broken physically, different devices tested at different times. And they're also broken in time. First measurements 2013, 2015. I don't think anybody's repeated those measurements. We're now 10 years down the track. 10 years of not testing the device is actually quite a long time. So I'll stole my thunder on that one. So when it comes to trying to evaluate the accuracy of timing devices, we're not actually in very good shape. There's not a lot of information that we can hang on to. At the moment, this is just still me working on things, finding about things. This is the kind of public-facing end where we just started to talk to some of the developers of these devices to try and understand, what testing they've done, how they think their device is performing. It's not definitive. I'm not trying to say this is correct. This is just to give you a flavour for what's going on. This all assumes the devices are still working and operating properly. And my Kiwi OSD was built in 2008. It's a pretty old device. How do I know it's still working properly? How do we know if any other devices are working properly when they're 10 or 15 years old? And in any case, none of this would be proof of traceability to UTC. It's just looking at the inherent characteristics of the device, some of the evidence we have to get a rough idea of how accurate we might think it is. So this is my table, and do not do anything with this. This is still very drafty. If you've got a different opinion, share your opinion. If you've got more evidence, let me know, because I'd love to know more evidence. This is just where I've got to based on the information that I could find. So we've got some of the time stamping cameras. They're able to operate in this microsecond range because there's a very short path between the PPS pulse and the circuitry that controls the camera. So potentially they can operate in that microsecond range. There has been some testing reported, but none of it looks like a full kind of calibration report. The QHY camera, they assert in the literature 1 microsecond, but I can't find any evidence on the website of any testing for anything. It just says microsecond accuracy. Now they're a manufacturer and they haven't put out a statement. Now they're in a position to be able to do this because they can actually go and do all these kinds of measurements. And if they wanted to, they could repeat them regularly and each year say, we keep testing our QHYs and this is what we're doing. But it's not available. So we just have to take that one at face value. Has been a little bit of testing on the QHY using Sexta and Exta, and that's stacked up to down to the 0.1 millisecond accuracy for that one. That requires some internal calibration. The rest of these devices, if they are working according to spec, if they are actually processing that 1 PPS signal properly, this is the kind of accuracy that we'll be able to expect from them. So your VTIs are down at 0.1 to 1 to 2 milliseconds. I've published a paper on some of the testing that I did on my methods of GPS flash timing, and we're at these around about 5 millisecond range, maybe a little better if things are going well. And then things start to get interesting. GPS flash timing is a lot of different ways people do it. Some people have strong protocols, some people have weak protocols. 5 to 20 millisecond range is about where I'm expecting most of those. And there's effects like rolling shutter that you have to deal with properly, otherwise you're just introducing other types of errors. Dave Galt has done some sterling work with some other people in publishing testing on various devices. He's got a very good paper on NTP, which is well worth looking at. In that they showed about 15 millisecond accuracy possible with NTP, network time protocol, when it's done well. I will note with those, and I'll talk about it some more, that requires your PC to be reasonably stable on its time. And not all PCs are equally stable. I've got a couple of PCs that are quite stable. I've got an older one that it's time for us to drift a bit once the load gets under there. So you can't just take this and apply it to your system because your system is different. You've got a different PC, different, you don't have the same bit. Someone can say NTP is 15 milliseconds, but that's their system. Your system is what you'll put together and how it operates. So the further away we get from these sort of self-contained devices, the more responsibility the individual observer has to take to show that their system and all the bits and pieces they've put together is actually working properly. The PC clock discipline, I'll be running a workshop on that. There's actually 3 or 4 different ways that this can be done, and they have varying time and accuracies. What they all have in common is they have the same types of issues around how PCs behave and how cameras behave for them to deal with. So there's a lot to think about. So please don't do anything with this. This is currently my rambles. my best attempt at where I am, and I'm not finished with the process. I want to talk to or find more information by some of the designers of this device, and just try and figure out basically how this is all working. There's another issue, and this is something that Dave Hewlett has raised, and those issues with the DDoS and data impact really come to the fore. Is how reliable is our device? And you have to ask, what could go wrong? How often does it go? And possibly most important, because Dave, a comment you've made is that you are more concerned with reliability than accuracy, to paraphrase what you've said. So, to some extent, you don't really care what the accuracy is, as long as you know that it is reliable to that accuracy. So a really important thing is, how do you know that something has gone wrong? How do you know when you write your report that there wasn't some timing area because something went wrong and there was nothing in your status lights or anything to tell you that something's gone wrong? And with some of these devices, we don't necessarily have a good handle on that. They might not be working properly and you might not know. Another thing is, how do you recover? Your device fails. Have you just lost your observation, or can you recover it in some way? So there's an example of some of the errors that could occur, and there's lots of errors that can miss. Some of these are down to the user. We have floated the idea of some kind of reliability classification, which maybe could go in a report, or maybe it could be another drop down in reporting form, and would give Dave Herald maybe some extra information that could be supplied along with the astrometry. This is just me floating ideas. A few other people have kind of commented on this and agreed or disagreed to different extents. But the important concept here is, when you go through these devices, some of these devices, there's no user input at all required. You turn the device on, it does what it's meant to do. Astral does this, and the DVTI CAM does this. When it switches on, it does everything. It provides timestamps. There's no adjustment required by the user. The QHY174 GPS, you actually have to do a little internal calibration on it before they say it's going to do the accurate times. So the user has to do something. So that's inherently less reliable. And then you get to our VTIs, and it's like, yes, they put a timestamp there, but then you have to process those timestamps. And in some cases, you have to manually put in information. So there's more things that can go wrong. By the time we get to about class 4, it's kind of fanning out into loads of different ways of doing things. And some of these you need to be quite careful with what you're doing to actually get to good times. Anyway, these are just some kind of ideas that are floating around. So some of you will have used maybe only one of these timing systems. Some of you may have used multiple of these timing systems. But this is basically where I've got to. So if I put on my trained scientist hat, someone who's published papers and all this kind of stuff, and I really put hand on heart, and is my timing system tested and calibrated? Are my times reliable? And from a scientific and technical perspective, we don't really have a known timing accuracy for a lot of our devices. I feel like I've just I feel like I've just farted in an elevator here. Sorry about that. Or lift, depending on which country you're from. Another point, if we want to be professionals and not amateurs, treat them like them, our time bases should be up to professional standards. Now that's quite a challenge, but I don't know if the professionals do this. Does anybody know?
Well, I guess it's no.
You'd be surprised. Yeah, sort of when I did my PhD in astronomy and stuff, and then when I went to work, it was actually more rigorous. I was business.
Yeah.
Than at the university.
Yeah, because the business is, if you're dealing with time, you have to actually comply with financial regulations on the time and accuracy of your computer service handling financial transactions. And if you get it wrong, you can get fined, or you could lose your license to trade. And that's a big incentive for people to do time. So often in the commercial sector, I think people may actually do it better, despite often academics look at themselves as doing better than the commercial. So I don't know if the professionals test and calibrate. I suspect that probably a lot of them, or most of them, don't when they're dealing with these times.
thinking right down Bell, so. No, I'm doing this. Just the thought that about 20 years ago, we did some astrometry of a fast moving asteroid. And Gareth Williams, I think, was involved in organising it. I did video. You did observations at Mount John with a camera where you had a shutter over the front of the telescope. So you can remember it because your times were out, and it was because you hadn't allowed for the time it took for the shutter to work. Switch the camera, so you know something you know that. I remember very well.
Well, we were doing some very fast tests. I mean, this is getting off topic, I think, a little bit because.
Well, I'm just pointing out at the time, and this is a real problem in all the. I mean, they recently did a test at the Allen Planet Centre with a fast moving thing, getting people to do the traditional astrometry so they could compare the astrometry with the times to pick up time difference.
Yeah, so that was talking about Michael Planet Centre having observers doing tests of fast-moving asteroids and getting a range of times for them. I think of the Michael Planet Centre recommendations for astronomy and photometry, they tell you to have an accurate time. I think they suggest maybe NTP or something like that. None of you will have looked at that list for a while, but I just wanted to try and do some research to have a look through it. But they don't actually have a tight time standard for their users. They kind of leave it up to them. Anyway, so there's an open question there. I'm not sure we're going to like the answer if we actually dig into it. That's why I'm into the rabbit hole. I'm still down the rabbit hole. I'm the white rabbit with the clock going down the rabbit hole, and I've not emerged at the top of this yet. So, you know, how can we actually show
can I just make one?
Yes.
We've got time for one comment. Just going back to Dave Hewitt's presentation on DART, it seems a bit of an indirect calibration of the timing of a whole bunch of different cameras that would have been used in those occultations. It does seem, given your concerns, that there is a good consistency in it. And anyway, if you look at the errors that are around the occultations versus the radar versus the other ground-based observations, so while there obviously are errors in there, they don't seem to be making too much of a catastrophic contribution.
Yeah, that's talking about the consistency. I think the Japanese ones were the most consistent, and they tend to use the same method of GPS flash timing with the same equipment. So they're consistent, but they could also all be equally wrong because they're using the same system. And that was a comment about John Broughton's observation. All the systems were using the times consistent, but they were all using the same system. So consistency can show that you're consistent, but it doesn't prove that your time is traceable back to UTC. It's certainly one way that you could do some self-checking. Compare yours with another observer with a different system. If you get the same result, it's, you know, it gives you some evidence that at least you're consistent, but it doesn't go this extra step.
That observation.
Yep. Okay.
Yeah, that observation back there compared to other methods of measurement puts occultations in a very small error place. So that there must be some accuracy in it.
Anyway, I'll carry on. Anyway, if we wanted to trace back to UTC, I'm not saying that we want to. From a scientific perspective, I think it would be a good idea to, but there may be alternatives. This is the kind of thing that we need to do. We actually need to figure out what our standards are and come up with some standard testing requirements and processes for that. It's no good everyone doing things differently. We need some form of reference timing device, and something like the stamp of approval or the new Irish GFT, I think, are suitable devices to be able to do that. We need to be able to distribute those reference times and designs so that observers have a consistent reference standards that they can use. We might actually be able to do unit testing of some common devices. So the likes of Astrid, it might be sufficient to test one or two devices, and then you can assert that all the Astrids have the same performance. Maybe for the DVI cam or the QHY, that's a possibility. But we also need individual users to start doing checks and calibrations on their own devices in some form, hopefully against the reference standard. And we also need some kind of ongoing monitoring, so we just keep an eye on this kind of stuff, so we know when things are going wrong. So, your camera failure, you wait at camera failure, IoT video time refinement. We need to actually keep an eye on this kind of stuff, because once we start to see problems with our equipment, we can have an opportunity to do something about it. We are so close to be able to do this. It's scary. We are now in the position we've greatly improved GPS flasher designs. The designs that Mark Simpson has put on, has gone to the trouble of really digging into those delays and helped pass the flasher.
The background.
Oh, sorry. We're really close to be able to do this. We've got improved GPS flasher designs. GPS flash timing is one of the main methods that we can use. Mark Simpson's stamp of approval in the IoT GFT using much improved GPS flasher designs. We've developed a better understanding of how GPS flash timing works over the last couple of years. We also have a better understanding of how all these cameras and systems work and how Windows PCs form. So we're actually getting into the position where I think we could actually do this ourselves. And of course, we've got some very smart, capable people worldwide that will be able to help us. But this is not an individual effort. It's not something that one person can do. Certainly not across all those camera systems. So I think we've got all these pieces available. It's just how we'll become to put this together. Sorry, I did something. So what about your timing system? How confident are you with your 10 or 15-year-old device? And how do you know? When Dave asked the question, it's not lining up with the astrometry, how are you going to answer it? And that's probably make a few people feeling uncomfortable. What you can do now, before maybe we establish something better, is get an independent time system onto your PC. And we'll talk about the PC discipline. So you've got multiple sources of time available, not just relying on one. That even with a VTI, you can do some basic tests with that to prove that you haven't got like a leap second or more than a second error on that. As was pointed out by Richard Brown, you can compare to different timing systems. You can both observe the same event. You can both do GPS flashes. GPS flash timing is where you actually start to get some real precision. We'll be covering that in the workshop a bit today. That gives us an opportunity to test. It'll currently be tested against an uncalibrated GPS flasher, or one we're not necessarily that certain in performance. But once we actually get going and get some of these reference time standards, we'll be able to do this and try and get behind this testing and calibration issue. If we're actually wanting to move into these areas where high precision timing is required for scientific needs, like DART, like these small asteroids and these kinds of things, we need to keep upping our game so that we actually have the technical and scientific rigor to be able to support these activities. We've seen how many other groups, their activity is basically dead in the water as a scientifically valuable one because it's been overtaken. We need to keep relevant. So it's about time to show that we know the time.
Thank you, Mark. We'll be looking to end lunch at 1:15, which is 25 minutes away. Are there questions online? Because the rest of us can collar Michael during lunch.
I think the workshop would be useful.
Yeah, so the workshop starts at 1:15. We've allocated an hour and a half for that. Happy to run the Zoom session through that, but given that people are spread out, I don't know how well Zoom land is hearing voices from the other side of the room. It's quite a noisy room, so we're hearing the whole damn building up here.
Yeah.
Well, we'll do what we can.
We'll see what we can do. Did you have a PowerPoint or any shared projected material for the workshop, or was it?
I do have some shared projected material. I do have some files to share in the room. There's links to the files in the presentation and stuff.
Okay.
So people offline will be able to follow along to some extent, depending on what they've got. The first part they should be able to follow along with if they want to.
Good. Okay, so we'll run Zoom, we'll record it, and we'll try and get that stuff through. But for now, we'll drop off until 1:15 NZST, which is 20-something minutes away. The food's been in the back of the room, making everyone very hungry. Quick, go and eat, and we'll see you again shortly.
Thank you.